There are 100 billion stars in our galaxy, the Milky Way, or maybe there are 200 billion, or maybe 400 billion. No one really knows. In the universe there are 100 billion galaxies, and as technology improves, that number could increase to 200 billion galaxies. No one is certain. At the start of the 20th century, there was only one galaxy, our own. After more than 40 years, Voyager 1 has left the influence of the solar wind and is heading for interstellar space. Most of its instruments have been switched off, and its nuclear battery is running low. It will be many thousands of years before it reaches anything other than interstellar debris. By then, the craft will be long dead. Cosmic distances are so vast that sending a probe to investigate anything beyond our solar system is not practical. The only realistic way we have of exploring the universe beyond our neighborhood is by examining the light that reaches us. The telescope is the main tool we have for this investigation, and for centuries astronomers have been building ever larger instruments to see deeper into the cosmos. In the 20th century, conventional telescope design reached its limit. Past 8 meters in diameter, the curved primary mirror becomes so heavy that it will sag. As it is aimed at different targets, its precise curve is distorted by the effects of gravity. In addition, any extra resolution gained by the larger mirror is not delivered because of atmospheric distortion. One way to solve both these problems is to put a telescope in space. The Hubble Space Telescope is the best-known example. While the absence of atmospheric distortion was a breakthrough, producing very sharp images, both operational and maintenance costs are considerable. And there are launch constraints on the size of a telescope that can be delivered to orbit. But engineers have developed a new generation of Earth-based telescopes with segmented mirrors that overcome the limits to size and can nullify much of the distortion caused by the atmosphere. The twin Keck telescopes on Mauna Kea in Hawaii were early adopters of this technique. Both have 10-meter mirrors, each in 36 hexagonal segments. Sensors monitor the mirror's shape, and actuators behind each segment continually correct for any distortions to the curve. The system is called active optics. A similar system that works at a more rapid rate monitors the stability of a bright guide star or an artificial guide star generated by a laser. The adaptive optics system reads wavefront changes in the atmosphere, then adjusts the mirror's shape to minimize any distortion. This image of Jupiter using adaptive optics rivals those captured by an orbiting telescope. Observatories are located at high altitude where the air is dry and there is no light pollution from nearby cities. The European Southern Observatory has clusters of telescopes at several sites high in Chile's Atacama Desert. At Paranal, 4 identical large telescopes each have 8.2-meter mirrors. They can combine their light using interferometry. In addition, 4 auxiliary 1.8-meter telescopes can link into the cluster. Collectively, they are the Very Large Telescope Interferometer, or VLTI. Visible light is just a small part of the electromagnetic spectrum. ESO has another facility northeast of Paranal on the Chinantur Plateau. Here an array of 66 radio dishes observe in millimeter and sub-millimeter wavelengths. They are linked and also function as an interferometer. Observing in the microwave part of the spectrum is particularly useful as these frequencies penetrate gas and dust clouds that remain opaque to higher energy signals. The more widely the telescopes are separated, the better the angular resolution they can deliver. This property led radio astronomers around the globe on a unique collaboration. If radio telescopes around the world could link up, perhaps they could see the unseeable. General relativity predicted bodies so massive with such strong gravitation that not even light could escape from them. They were called black holes, and at first they were regarded as a mathematical anomaly. But evidence mounted suggesting that black holes were more than just a theoretical curiosity. At the center of some galaxies, light far more intense than could be expected from stars has been detected. Massive bodies such as young stars attract diffuse matter which begins swirling and flattens into what's called an accretion disk. Just as planets orbit stars, it's now accepted that galaxies orbit supermassive black holes. By 2009, an international collaboration between 8 different telescopes had coalesced. They aimed to capture an image of the supermassive black hole at the center of Messier 87.
So, for this experiment it was clear that we need expertise from completely different areas, and so we needed someone with imaging capabilities. We needed someone with numerical relativity capabilities.
The project was named the Event Horizon Telescope. Instruments in North and South America, Europe, Hawaii, and even in Antarctica would unite to form a telescope with a virtual diameter equal to the Earth. None of these facilities was designed to work as part of such a large array, and the technical difficulties facing the team were immense. In April 2017, the EHT was scheduled to make a series of coordinated observations of the heart of the M87 galaxy. Each observatory had been equipped with its own atomic clock, as all data had to be meticulously time-stamped. Good weather had to happen simultaneously at each site, and a go/no-go decision was made several hours before each observation. During the observation period, 5 petabytes, that's 5,000 terabytes, of data was recorded. The hard drives upon which it was stored weighed half a ton. In April 2019, the Event Horizon Telescope team released their image of the active center of the M87 galaxy. At its heart was the silhouette of one of the largest black holes we know. It's roughly 38 billion kilometers across, the diameter of our solar system. Its mass is 6.6 billion times greater than our Sun. After predictions flowing from the general theory of relativity more than 100 years ago, the world finally has proof that black holes do exist. Since Copernicus proposed that the planets orbited the Sun, astronomers have speculated about planets orbiting other stars. Advances in telescope technology allowed researchers to see dips in the brightness of stars that could only be caused by a transiting planet. A different method monitored the spectral shifts in a star's light caused by a consistent change in its position. Again, only explicable by an orbiting planet. Another star, 40 light-years away, has a greater range of possibilities. TRAPPIST-1 is an ultra-cool red dwarf star orbited by 7 planets, all of them close to Earth in size. At the moment, around 3,800 exoplanets have been catalogued, and that number continues to grow. In 2018, the satellite TESS was launched to search for more exoplanets. There's a gap in knowledge that some cosmologists find embarrassing. When quantifying the speed at which galaxies rotate and the amount of mass they contain, there's a baffling mismatch. Astrophysicists came up with the dark matter hypothesis. This is not just matter that doesn't glow, it is matter that interacts with nothing else. The only influence it has is via gravitation. New generations of telescope are being built to help researchers answer some fundamental questions about the laws governing the universe. But it seems that cosmology has reached a stage where it is just discovering how little we know about what lies beyond the solar system.